शकता. थर्ड इयरला ही सेम पॅकेज.
Hello all, can you hear me?
Yes,
Hello,
ma'am. Hello.
can you hear me, all of you?
Yes, ma'am.
Okay,
Yes.
okay, I will mute all participants so that there will not be disturbance, okay? So today we are going to study problem of particle in rigid box. Rigid box, or it is also known as infinite potential well. So let us consider how potential is defined through which particle is moving. As we had discussed earlier, in every quantum mechanical problem, potential is given to you. Potential is defined, and you have to find out its wave function and total energy of the particle. In classical mechanics problem, force acting on the particle is given to you. Its initial position and velocity is given to you, and you have to find out its final position and velocity. In quantum mechanical problem, potential energy is given to us. So in this problem, potential energy is infinite for the region of x less than or equal to 0 and x greater than or equal to L. And potential is 0 for region x is in between 0 to L. Only within this region potential is 0. So if you remember the steps which I have given to you, I have given you procedure how to solve quantum mechanical problem. There are 5 steps. In step number 1, you have to plot a potential energy versus x graph. So here, this is the graph of potential energy versus x. In between 0 to L, potential is 0, and outside this region, potential is infinite. You cannot plot infinite point having infinite y-axis. It is shown with dotted lines. It is going up to infinity. So step number 1 is over. Now what is step number 2? Step number 2 is you have to divide complete space into different regions depending on value of potential. So here it is very obvious that this complete space you can divide into 3 different regions. X is less than 0, potential is infinite, so region number 1. X is in between 0 to L, so potential is 0 in region number 2, and x greater than L, potential is again infinite, region number 3. So step number 2 is also over. Now you have to consider step number 3. I have defined different regions here. Now consider step number 3. According to step number 3, you have to write Schrodinger wave equation in each region. Now potential energy is independent of time. It is dependent only on space coordinate x. And therefore you have to apply Schrodinger's time independent wave equation, which is del square operated on psi plus 2m by h cross square E minus V operated on psi is equal to 0. And for one-dimensional problem, this is one-dimensional problem, we are considering that particle is moving only along x-axis. Therefore, Laplacian operator del square will be simply d square by dx square. So d square psi by dx square plus 2m by h cross square E minus V operated on psi is equal to 0. Call this as equation number 1. You have to consider each region. So consider region number 1 first. In region number 1, V tends to infinity. Therefore, total energy E will also tend to infinity, because total energy is nothing but kinetic energy plus potential energy. In such region, particle cannot exist. Probability of finding particle will be 0. Therefore, psi1, that is wave function in the first region, should be 0. Because wave function is related with the probability. Mod psi square represents probability density of finding the particle. That is probability of finding the particle per unit volume. Since there should not be 0 probability of finding the particle where potential is infinite. Therefore, psi1 should be equal to 0. Similarly, region number 3 also V tends to infinity, E tends to infinity. Therefore, psi3 should be exactly equal to 0. That is, wave function in the third region should be 0. What does it mean? It means particle is restricted only in second region. It cannot penetrate the walls of the box. And therefore, it is called as a rigid box. Walls are rigid. Particle cannot penetrate those walls. Or it is also known as infinite potential well. Particle is trapped in that potential well. It cannot come out of that well. So we have to now concentrate only on region number 2. In region number 2, potential is 0. Therefore, equation 1 will become, you have to substitute V is equal to 0 and psi is equal to psi2. D square psi2 by dx square plus 2m by h cross square E minus 0 operated on psi2 is equal to 0. Therefore, d square psi2 by dx square plus 2m by h cross square E operated on psi2 is equal to 0. Let us consider the constant 2m by h cross square operated on E is equal to k square. All of you know h cross is nothing but h by 2 pi. We are considering this constant as k square and not simply k. Reason is written here. M is mass of the particle, which will be positive. H cross square is positive number. H cross square is positive number and E is total energy of the particle. In this particular problem, total energy E is positive because potential energy is zero. Total energy consists of two parts, kinetic energy plus potential energy. Since potential energy is zero, total energy is simply equal to kinetic energy, which is equal to 1/2 mv square, which will be always positive. Therefore, to indicate that this number is strictly positive, we are considering it as k square and not k. So, differential equation will become d square psi 2 by dx square plus k square operated on psi 2 is equal to 0. And this is second order ordinary differential equation. It will possess, according to theory of differential equations, it will possess two linearly independent solutions, which are e raised to ikx and e raised to minus ikx. E raised to ikx is nothing but cos kx plus I sin kx, and complex conjugate of this number is, you have to replace I by minus I. So replacing I by minus I, you will get e raised to minus ikx is equal to cos kx. Here also you have to replace I by minus I. So minus I into sin kx. Therefore, most general solution of this particular differential equation will be linear combination of these two. Linear combination means you cannot change these two original functions, can take two arbitrary constants a and b and linearly combine these two solutions or functions. So linear combination of these two will be psi 2 of x is equal to a into e raised to ikx plus b into e raised to minus ikx. Call this as equation number 3. So we got psi 1, psi 2 and psi 3. Psi 1 and psi 3 are 0 and psi 2 is non-zero, which is a into e raised to ikx and b plus b into e raised to minus ikx. Now let us consider step number 4. You have to apply boundary conditions. Boundary conditions means conditions imposed on wave function psi. We have considered 4 conditions. First very important condition is that wave function psi should be single valued function. Psi 1 at x is equal to 0 is equal to psi 2 at x is equal to 0. Wave function psi 1 is 0 and wave function psi 2 is nothing but this linear combination. Find the value of this at x is equal to 0. Therefore, a plus b is equal to 0. Therefore, b is equal to minus a. Put this in equation number 3. You will get psi 2 of x is equal to a into e raised to ikx minus a into e raised to minus ikx. Now you have to multiply and divide by 2i. If you multiply and divide to make this in compact form, we are doing this procedure 2ia into e raised to ikx minus e raised to minus ikx divided by 2i. Therefore, psi 2 of x is equal to 2ia sin kx. That bracketed quantity is nothing but sin kx. Now you have to apply single valuedness condition at second boundary. Actually, for this problem, there are two boundaries. If you refer to page number 17, refer to page number 16, sorry. Consider page number 16. In this problem, there are two boundaries at x is equal to 0 and at x is equal to L. Here, if you consider in region number 1, psi 1 is 0 It has only one value for psi1. In region number 2, psi2 is equal to a into e raised to ikx plus b into e raised to minus ikx. So there is possibility that psi1 and psi2 will not match at this boundary, and therefore we are applying single valuedness condition specifically at this boundary. Similarly, there is non-zero probability that values of wave function may not match at second boundary also. So you have to apply boundary condition at this boundary, that is psi2 at x is equal to 0 should be equal to, no, not x is equal to 0, x is equal to L, should be equal to psi3 at x is equal to L. Psi2 is approaching from this side and psi3 is approaching from this side. So both these psi2 and psi3 should have single value at x is equal to L. So these are called as boundary conditions. Now let us again go back to our original page number 21. Psi2 at x is equal to L is equal to psi3 at x is equal to L. Therefore, 2ia sin kl is equal to 0. Either a is equal to 0, this is product of two numbers. So when product of two numbers is 0, any one of them should be 0. So either a is equal to 0 or sin kl is equal to 0. If you consider a is equal to 0, if you substitute a is equal to 0 in this, psi2 of x will be 0 within the entire range from 0 to L. Means inside the box, wave function will be 0. Already wave function is 0 outside the box. Psi1 is 0 and psi3 is 0. So if wave function is 0 even inside the box, then probability of finding the particle throughout the space will be 0 and there is no need to solve this problem. So you cannot consider a equal to 0. Means psi2 should be 0. Means sin kl should be equal to 0. If you consider sin kl is equal to 0, kl should have values equal to n pi. Sin n pi is 0, sin pi is 0, sin 0 is 0, sin 2 pi is 0. So n will have values 1, 2, 3 onwards. Now here you may have questions why n is not equal to 0. So answer is given in this box. If you consider n equal to 0, kl will be 0. Means either k equal to 0 or l is equal to 0. K cannot be 0. Again same reason. If k is equal to 0, psi2 of x will be 0 everywhere inside the box. Means probability will be 0 even inside the box, which is not acceptable because particle exists inside the box. And if you consider L is equal to 0, it is meaningless concept because L is length of the box. If I tell you that I will give you gift of jewelry box having length 0, it is meaningless. So L cannot be 0, therefore KL cannot be 0, N cannot be 0. Therefore K is equal to N pi by L, and therefore psi2 of x is equal to 2ia sin n pi by L. We have found value of K, and this K is related with E, energy of the particle in which we are interested. So 2me by h cross square is equal to K square. Now consider page number 23. So 2me by h cross square is equal to k square, which is equal to n square pi square by L square. Therefore, En is equal to n square pi square h cross square divided by 2ml square, where n is equal to 1, 2, 3 onwards. Because n equal to 0 is not allowed. Reason we have seen. Here, En is called as energy eigenvalues of particle trapped in infinite well. Eigen means specific. These are the specific values. Only these values are allowed. And n is called as principal quantum number. N, smallest value of n is equal to 1. Even if you substitute n equal to 1, E1, which is ground state energy, will be pi square h cross square by 2ml square. For n equal to 2, E2 is equal to 4 pi square h cross square by 2ml square, which is called as first excited state energy. Here you should remember one thing. For ground state, n is not equal to 0, n is equal to 1. Many students make mistake while calculating ground state energy. And therefore, first excited state energy will be for n is equal to 2. E2 is equal to 4 pi square h cross square by 2 ml square, which is first excited state energy. N equal to 3 is second excited state energy, which is 9 pi square h cross square by 2 ml square. This shows that energy values are quantized. Quantized means particle cannot take any value continuously. All values are not allowed. Only specific values are allowed. Only specific values are allowed. So this is called as energy eigenvalues. So we have solved half of the problem. Now let us consider step number 5, which is nothing but normalization of wave function. That is last step. Why normalization condition is imposed? It is imposed because total probability of finding the particle throughout the universe should be equal to 1. Mod psi square represents probability density, that is probability of finding the particle per unit volume, in this case per unit length, because we are considering one dimensional problem. So mod psi square into dx will give you actual probability of finding the particle in the length element dx. So if you integrate it throughout the complete space, it should be equal to 1, which is known as normalization condition. So your wave function should be normalized wave function. Your wave function should be normalized wave function. So this we can divide into 3 different regions, because we have 3 different regions: minus infinity to 0, psi 1, so mod psi 1 square dx. Then 0 to L second region, mod psi 2 square dx, plus L to plus infinity mod psi 3 square dx, which is equal to 1. Therefore 0 plus mod psi 2 square dx plus 0 is equal to 1. Therefore 0 to L mod psi 2 square dx is equal to 1. What is mod psi 2 square? Mod psi 2 square is nothing but psi 2 into psi 2 star, where psi 2 star is nothing but complex conjugate of psi 2. psi2 is 2ia sin n pi by L into x. Therefore, psi2 star is equal to, you have to replace I by minus 2ia, replace a by a star. We don't know whether a is real or complex. If a is real, a is equal to a star. But if a is complex, you have to take care of it, and therefore we have considered it as a star into sin n pi by L into x. Therefore, mod psi2 square, multiply this and this, 4 mod a square sin square n pi by L into x. Consider page number 25 and 26. Therefore, integration from 0 to L mod psi2 square dx is equal to 1, which will become 4 mod a square sin square n pi by L into x dx is equal to 1. Therefore, 4 mod a square 1 minus cos 2 n pi by L x by 2 into dx is equal to 1. Therefore, 4 mod a square by 2, integration of 1 will be x, and integration of cos 2 n pi by L into x will be sin 2 n pi by L by 2 n pi by L, limits of the integration from 0 to L, which should be equal to 1. You cannot directly find out integration of sine square. That's why using trigonometric formulae, we have converted into linear trigonometric function. Once you convert it into linear trigonometric function, it is very easy to find out integration. So, value of x is L minus sin 2 n pi by L into x, which is equal to L, minus 0, lower limit is 0, 0 minus sin 0 is equal to 1. Therefore, 2 mod a square L, value of sin 2 n pi is equal to 0, sin 0 is already 0, which is equal to 1. Therefore, 2 mod a square L we have to end the lecture within 10 minutes. We are at the end of the problem now. 2 mod a square L is equal to 1. Therefore, 2 mod a square L is equal to 1. Two mod a square L is equal to 1. Therefore, mod a square is equal to 1 upon 2L, which indicates a is real. Because L is real, L is length of the box, which is real number. So mod a square you can consider as a square, simply a square. Therefore, a is equal to plus or minus 1 upon under root of 2L. This is called as normalization constant. Therefore, psi2 of x is equal to 2i by under root of 2L sin n pi by L into x, or psi2 of x is equal to minus 2i by under root of 2L sin n pi by L into x. Although these are two different functions, mod psi2 square, if you find out mod psi2 square of this and mod psi2 square of this, it will be same, because this is the complex conjugate of this and this will be complex conjugate of this. Consider normalized wave function psi2 of x is equal to 2i by under root of 2L sin n pi by L into x. So it is dependent on n. It will have different function for ground state, first excited state, and so on. So ground state wave function will be n is equal to 1. Psi2 of x is equal to 2i by under root of 2L sin pi by L into x. First excited state wave function n is equal to 2. psi 2 of x is equal to 2I by under root of 2L sine 2 pi by L into x. Second excited state wave function n is equal to 3. Psi 2 of x is equal to 2I by under root of 2L sine 3 pi by L into x. Okay. Now let us consider plot of psi and psi 2 square versus x. Now to plot this wave function, let us consider 2I by under root of 2L is equal to 1. So that it will be easier for us to plot the wave function. Therefore, psi 2 of x, n denotes state. N equal to 1 is the ground state, n equal to 2 is the first excited state, and so on. Sine n pi by L into x. Ground state wave function is psi 2 1 x is equal to sine pi by L into x. Psi 2 0 is equal to 0. Psi 2 of L by 2 is equal to 1. You have to simply substitute x is equal to 0. Sine 0 is 0. If you substitute x is equal to L by 2, sine pi is 1. And if you substitute x is equal to L, sine pi by 2 is 1. And if you substitute x is equal to L, sine pi is 0. First excited state wave function is psi 2 2. Now n is equal to 2 for first excited state is equal to sine 2 pi by L into x. Psi 2 2 0 will be 0. Psi 2 2 L by 2 is sine 2 pi by 2 L by 2 sine pi is equal to 0. Psi 2 2 of L is equal to sine 2 pi by L, which is equal to 0. So you are getting all three values are 0. Here we have considered plot of ground state. Psi 2 0 is 0. This is 0. Psi 2 L is 0. At x is equal to L it is 0. And at L by 2 means at the center it is equal to 1. So it is like half sine wave. And when you consider first excited state, we are getting all three values 0 for 0, L and L by 2. So it cannot happen that wave function will be 0 everywhere. So let us consider the values at L by 4 and 3L by 4. So at L by 4 value will be 1 and at 3L by 4 minus 1. So it is like complete sine wave. And when you consider mod psi 2 square, it will be simply square of this. It will be simply square of this. This negative part will become positive because mod psi 2 square is always positive and real. We have considered this when we considered physical significance of psi. Mod psi square represents probability density, probability of finding the particle per unit volume. So it should be always positive and real. Mod psi square versus x indicates probability of finding the particle at center, which will be maximum for ground state. Here probability is maximum at the center, and which is not obvious. Classically, if you solve the problem, probability of finding the particle everywhere inside the box will be same. There is no reason why probability is maximum only at the center. And therefore, quantum mechanical treatment is entirely different. We have seen even in the energy values are quantized, which does not happen in classical mechanics. In classical mechanics, energy spectrum is continuous one. Try to understand both these graphs because we are going to consider next problem will be non-rigid box, that is particle in infinite potential well. Here outside the box, probability of finding the particle is 0. We have artificially introduced boundary conditions, single valuedness conditions. We have made the wave function 0 at the boundaries. Therefore, everywhere you will find 0 at the boundaries for every state. Here also 0, 0. Probability is 0, 0. 0, 0. Okay. So considering this, we are going to solve problem of particle in non-rigid box or finite potential well. And that problem is, we are going to not solve quantitatively, because it is included in your syllabus, only qualitative discussion is included. So try to understand this graphs. And with this, the problem is over.